All right, so thank you for the invitation and for the introduction. I'm going to, so I'm really an applied mathematician, probably a statistician. I would say that for some reason found myself doing electrical engineering. And I'll do something a little bit different. So I'm going to tell you about a hammer that we've been using, and with which we can explain all sort of interesting phenomena in power markets. And as you'll see, this is a pretty big hammer. And I'm glad that I'm the last speaker because there's no upper bound, so in the next 2.5 hours.
You can keep talking as long as you want. We'll walk
So this is the outline. What I'm going to do is I'll start with some introduction, talk a little bit about the dynamics. And this talk is really about continuous time markets, it's about dynamics. Then I'll show you all sort of interesting results. So market deregulation, I don't need to introduce it too much, but I would like to mention something. That originally when the regulation started, then it was hoped that it would lead to efficiency, availability, better investment, better predictability of prices, and lower volatility. That was originally the plan. That's so you know, this was hoped for. You'd tell me if this happened. Regarding successes or failures, well, I mean, you know, maybe Texas is a success in the States, maybe PJM is a success, maybe MISO, we can all argue about that, but quite a few failures and a lot of market manipulation. I tell you, if we'll stop the recording, I can tell you a bit more about current market manipulation that is going on. Or you'll buy me a drink later. So this is just some example of some really interesting phenomena that happened in the last few years. I didn't put the graphs from PJM and ERCOT recently, but they have some pretty interesting things happening in the last month or so. So we have huge price cap, huge price surges, like we see in Illinois and I guess in the Eastern Interconnect. Many other places we see negative prices. That's happened in West Texas. Actually, the prices are negative about once or twice a week now. Negative prices in Australia, in the Netherlands, many other places. So we see on the one hand huge price spikes. We see on the other hand negative prices. Something is not working properly, and we want to understand that better. Well, we can.
Price volatility by itself doesn't imply anything about efficiency or.
Exactly, we'll see that shortly. But it's a bit strange that you see such a. This is the only commodity, by the way, that is so volatile. So if you talk to traders, and you know they'll just tell you we are one trade away from being on the street. So this is the most volatile commodity on the planet.
Onions in India, actually. That's true.
So just a little bit about the markets. Power markets are very different than traditional markets. So you know all about the things that are written here. This is sort of a typical curve of trade curve. I just want to mention two things which we haven't discussed today. One is the outages. So there are lots of outages, both planned and unplanned. It is estimated about 10% of the units are not working at any given time for some reason or another. Maybe that's a little bit exaggerated. I would also want to mention strategic behavior by market participants. So market participants, especially the large utilities, do behave strategically. That's something that we see in real data, and whoever says otherwise is, you know, a dreamer. So this is something that we want to understand better. And if we'll ever go to the direction of a smart grid with a market structure, whether it's prices to devices or some other market structure, this will happen. I mean, there will be strategic behavior, and we need to face it and figure if we want to do something about it. Okay, let me just say something about intermittent supply. So we heard today 40% capacity factor. I think that's largely very optimistic. We have wind. We have lots of wind in some places. It's happening big time in Germany, in West Texas. In some places, other places in Europe, Nordic countries, in Greece too. It's happening big time. It's not very efficient. This is a typical capacity graph over time. So this axis is time. This axis is production. Not great. Nuclear phasing out. I think in all of the Western world, except for England. Well, we're there. By the way, the price is going to be, I would say, exuberant. per megawatt, but never mind. So we have different types of supply, our stable supply, less stable supply. By the way, in Israel we found gas, so we don't care about all those things anymore. And let me just tell you a little bit about what I do. So as I said, I'm a applied mathematician more than anything else. We create mathematical models. Everything that I'm going to say today is under the following restriction. A model is a model is a model. We don't believe the models are true. We build simplified models, and we hope to be able to explain things in a form that will not aggravate people that understand the material better than us. It's a really nice sandbox for trying ideas, and we also do a lot of data fitting, which I will not discuss today. So those are the principles of modeling that we're using. One, to tractability. Most of the things that I'm going to say today are going to be analytical. So we have been able to get analytical results under the restrictions that are for a particular model. And of course, we want to balance complexity and expressiveness, and whenever we need to explain something, we use Occam's razor. So we use a fancy math, and what I want to do today is to explain to you the model that we're using, and what kind of results one can hope to achieve, and what is the meaning of those results. So that's the kind of assumption that we make. We know that generation cannot increase instantaneously, so there is friction in supply and demand. Supply and demand are coupled by price, and the process is dynamic. So the emphasis here is going to be on the dynamic nature of the process, on the depends in time. And our hammer is stochastic differential equations. So I'm not going to give you a primer on stochastic differential equations. This really will take 3 hours. But I'm going to show you a tool that can be used to get some interesting results. And there are some questions that we're going to provide answers. So one of the questions is what will happen with more wind penetration, wind or solar in other places. The second question is, yeah.
I'm trying to follow, but if it's going to be stochastic differential equations, could you please fix the resolution problem of the screen? It's light or...
It's flickering. Stochastically. It seems, is it better now? But there is a connection problem here.
It's a frequency or resolution.
Yeah, it's my computer.
Go to system preferences. Detect displays and all of that.
Did that.
Where's the detect displays? I don't see it there. Huh?
Oh, it's a built-in display. Is it better now?
Seems to.
Right. So now everything is going to be much clearer. I'm going to talk a little bit about how much wind we can sustain, and then about the price classes. Should we have different price classes for different sources of energy? Should we have a different price class for ancillary services? And then finally, I'm going to talk a little bit about something that I don't really know the answer to, and that's whether we're going to see price oscillations with many players. And I'll argue that it might be possible not to see price oscillations. So the way we model the system is with dynamics. We define a stochastic process for demand, for supply, and for intermittent supply, and also there is a price process. So all those are stochastic processes. And the idea in modeling a market with friction is that we model just a change. So the demand change, this is just a fancy notation for writing the difference in the demand equals a function of the current demand, the price, plus something that is stochastic. So for those of you who don't know stochastic differential equations, which I assume is most of you, this is just writing some constant times a Brownian motion or just a random increment. So this can go up or can go down. So we have the demand change and the supply change. And the friction is modeled by the fact that we assume that the function fd and fs that control the demand and supply have bounded derivatives. So it cannot change too rapidly. Okay. And we also have intermittent supply. That's sort of the wind. So this is and the differential in the supply of the wind is a function of anything but the price. So it can be the current wind, and also some parameter, but it's not a function of the price in any case. So the wind does not care about prices. Those are some standard assumptions, monotonicity assumption of the changes. And just if you wish, you can think about a very simple linear function of the form f for the function f for both supply and demand. So this is our model. The model, I'm assuming that the increments are small, but stochastic. And we assume that there is also an ideal market maker. If you like, this is Mr. Market. This is the invisible hand. And this is the invisible hand observer prices, demand and supply, and sets the price as a control. So this is how the prices are going to change. They're going to change by it's a differential function, and it's not going to change by too much. And of course, this is an idealization. So the prices do change, but we think that this is a good idealization. You can argue whether or not this is a good one, but this is what we have chosen, so we can do the math. Let me just tell you what is the loss here. So the loss is the natural economic loss. So for the demand side is how much how you lose by how much you pay. So you pay the price times the supply, both the standard supply and the wind supply. You gain, so this is a minus sign by how much you actually get, and you pay the blackout cost. That the supplier's loss is the cost of supply minus how much it gets. I look at loss just because I'm a pessimistic person, so I also think about losses rather than rewards. And then there's an intermittent supply, which is very similar to the supplier, but the cost is different. And those are derived some standard assumption on the cost functions. These assumptions, of course, are bogus, but still they make sense, and they're technical as far as we're concerned. So the social cost, that's something that is important to understand. We take expectation because we have a random process, and then we take what will happen from now ad infinitum. So from now until the end of time, we have the e to the minus delta t. This is just a way to discount the future. It's not really important what you write here, but this is just to make the math work out. And this is the social cost. So we sum up everything, and all the payment disappear. So what we have here is a stochastic process. We have a cost function, and now what our objective is to find a control law that minimizes the social cost. So we take the standard economics approach, and we try to find a control that would minimize the expected cost for the system. And now this looks like a classical control problem. And some of us are control people, so we know how to solve it. And when you want to solve it, you can, if you make a further simplification and you assume that you have a linear structure here. So this is a linear structure for the state space. The state is demand, supply, and price. And because we cannot control wind, we can omit it. Then we need to solve an equation known as a Hamilton-Jacobi-Bellman equation. Whenever I write this equation, you don't need to try to read it. It just tries to show you what is the kind of math that is involved. Don't try to parse it. This is just a PDE, so it's a partial differential equation. Not very hard, not very easy. This is just a PDE. This PDE has a solution, and it is unique, which is a nice thing. So in principle, we should be able to solve it. And if we solve it, maybe we can say something about the solution. So this particular HGB has some, not going to get into the technicals, but it's not so easy. There are some discontinuities in it. So you need to use some techniques that is known as viscosity solution, but let's ignore that. What you eventually get is that the optimal control, the optimal price change, has this form. This is known as a bank-band control. So basically, the price has to go up or down to the maximal allowed level. But what's important for us is a solution exists, it is unique, and we cannot find it usually. So we have good news and bad news. There is a solution, it is unique, cannot find it. Okay. But what can we do? So since we're control theorists, we know that there is one problem that we know how to solve. Yes?
So is one side get control or two sides get control?
What do you mean? I just control the price. So the reason the market maker only control the price, increasing or decreasing it.
So you try to control that?
Yes. So you can lower the price.
So you get lower switchboard there.
That's right.
Steeper bottom.
That's right. So what we know how to solve is what's known as LQG control. So we know how to solve linear systems with quadratic cost. So that's what we're going to do. So we'll assume that we can write our system, our cost function. Remember, we had here all those expressions, so we're going to collect them together. And then the last term that we have here, that's some constant, which you call the volatility coefficient, times the price difference. So this is a sort of a pretty general approach. This Q here that we have is a function of the wind supply, and similar is D, and it turns out we can capture fairly diverse dynamics with this system, and we also assume that the dynamics are linear. This is not a bad assumption because you can linearize near the important areas or near the working point. So this is our assumption. And now basically it's more fancy math. Again, don't try to parse it. What's important to understand is that you need to solve some partial differential equations, and if you do that, then you can compute analytically the optimal control. So now we're in a situation where we have under some assumptions we have the optimal control. Good. So we have the optimal control. We can simulate it. We can understand how it behaves. So let's try to say something which is not so simple. So let's look at two fundamental properties. One is the efficiency. So this is the efficiency of the market. This is minus the cost function. This is the volatility. So the efficiency you already saw before. This is basically how much the social cost is going to be. The volatility is simply just the price changes. So here's a theorem. The efficiency is the decreasing function of the volatility coefficient. So in the problem that we had before, the larger the volatility coefficient is, let me just, this is the volatility coefficient here. It multiplies the price control. The less efficient the system is going to be. Okay, so that's not surprising, right? Because if I really care about volatility, then I probably care less about efficiency. But just to show you how it looks, so this is here we see a graph. This is a simulated system. Demand and supply are in blue and yellow respectively, and red is the price. And you see that when you have a small volatility coefficient, then the price goes berserk, and when you have a relatively large volatility coefficient, you have very nice smooth curve. So this is not surprising. All right, but here's a theorem that is a little bit more interesting. So let's look at the graph of efficiency versus volatility. So the point that you want to be in is here. So you want to be in maximal efficiency and minimal volatility, but you cannot. So there is a fundamental trade-off between efficiency and volatility. Perhaps not surprising, but for some systems you can actually compute it. So you can compute the curve, and you know that there is no control that will get you above this curve. So if you want more efficiency, you have to sacrifice volatility, and vice versa. And this point here, the point of maximal efficiency, is a point of maximal volatility as well. And the point of no volatility is at the point of minimal efficiency. So if you're working with a fixed price market, well, sorry for that, you're not going to be very efficient. And if you're working with a completely real-time price market, well, you're going to be efficient, but prepare for a super volatile market. That's your choice, but you cannot have both. Okay. So let's look a little bit let's look a little bit more carefully about wind. So here's a possible equation for the wind process. This is known as the Ernst and Uhlenbach process. It's something that is mean reverting, so it's going to go back to some expected level. I hear from people that understand something about wind that this is a relevant model. So, and let's assume further that the marginal cost of wind is much cheaper than other sources. That's also something that I understand is very reasonable. So let's look at the efficiency without the intermittent supplier and with the intermittent supplier. So what is the next theorem? So it's a little bit complicated, but it says that there is some fundamental limit, there is some fundamental number, such that if you have more volatility than this number, then basically you get less efficiency with the intermittent source. So this is something which is counterintuitive. You would expect that the intermittent source would always play in your favor. But it turns out that it's not, because supply and demand, well, once you have enough intermittency, then the supply of demand cannot catch up. And the prices shoots up, and the sort of normal players, the non-intermittent one, cannot follow through. So if you add cheap, highly volatile wind generator, eventually you will get reduced efficiency. So that's the first conclusion that is not really, was not really expected. Now, what do you do then? Well, what you do is you add ancillary services, right? So you add some fast producer that can compensate for the wind. So how would that look? You have a new supply source. Let's call it ST of A, and the dynamics here are not stochastic. So this ancillary service really kicks in whenever you want. This is not a stochastic equation here. So it's controllable. It's deterministic, non-stochastic. Think oil. And the price dynamic here that we have two prices. So we have the price for the market, and we have the price for as ancillary services. And we assume that this ancillary service is priced at the marginal cost. So this is more or less what is happening. And its loss is the cost of producing minus what it gets is the ancillary price, not the price of everything else, times how much it produces. So now we can go through the same motion that we went through before. We can do exactly everything that we had before. The social cost is going to be a little different. Now we have the cost of producing the ancillary services. Now we need to control for the volatility of both the standard price and the ancillary price, and our control is we have to control both the standard price and the ancillary price. So we can go through everything. I'm not going to go over it. You can still solve. There is another HJB equation. We can solve it, and basically we can find out the result. So the result is that if you have ancillary services, you'll be more efficient than without ancillary services. That's pretty much expected, but this will happen for every RE, so for every volatility coefficient. Now, that's I think pretty well expected. But then there is something which is interesting. So let's suppose that you say, well, you know what, I don't care about volatility. I want to be, in the best American way, just markets. Well, in that case, that's fine. That's your decision. But the efficiency with and without ancillary services will be the same. But the cost, the social cost, is going to be slightly higher. So basically, once you say that you don't care about volatility, there is no point in adding an ancillary services. Okay? If you should add ancillary services only if what you say, well, I really care about volatility. All right, so let's have some sort of an interim conclusion here. So if you want to add an intermittent supplier, that's great. It's the cheaper, you get cheaper power, but increased volatility. And then if you have enough intermittent power and enough stochasticity, then performance starts dropping. And you can offset it to some extent with fast, expensive, and deterministic supply. But now you can ask me, well, how much ancillary do I need? And how much wind can I sustain? So this is something we don't know how to answer. We know how to answer it for some models. And so we did some simulations. This is just to show how we do simulations. We basically run many simulations of stochastic processes. And this is just an example of what we get. So this is a market with 5% wind penetration. This is a sort of result that you expect to get. You have demand, you have supply. You have the intermittent supply, which is here. It's kind of flow, and this is how the price would look like. This is a market with 30% wind penetration. That's just going to go berserk. And the price is going to go all over the place, even just with 30% penetration. And if you'll add ancillary service, then in this case where you don't care so much about volatility, the price is going to go down. The ancillary service here, this is a price and purple is the price of the ancillary services. When you do care a lot about the volatility, well, then you can just you're going to suffer much higher spikes of the ancillary services prices, and you can make the price very, very calm. So you can make, if you're willing to pay a lot in ancillary services, you can perhaps not surprisingly get a reasonable non-volatile price curve. So, and this is just an example of you comparing what happens when you have a single price and when you have dual price for the same volatility coefficient. As you can see, the ancillary services, when there is a different price, smooths things significantly. So this is again just some simulations. And this is, I think, really an interesting graph here. So what happens if you have multiple classes of prices? In the blue is a graph we saw before of the trade-off between volatility and efficiency. Now we decide to add another graph for having a special price for ancillary services and a price for the normal services. And you see that the situation when you have two prices dominates. So for every level of volatility, you're going to get something which is more efficient. And vice versa, for every level of efficiency, you're going to get something which is less volatile. So if you're asking me, do I need to have two different prices, one for ancillary services and one for the standard grid, the answer is always. So this is a comparison of the trade-off. Okay. So let's try and get some answers to the question that we had before. So what happens with more wind penetration? So this is like the joke, right? First it gets better, then it gets worse. And there is really an issue of how bad it's going to get. The answer is going to be if you have a fully renewable grid without storage, there will be no grid. So just volatility is going to crush it. The question two is, can we have stable prices and have efficient markets? So here the answer is no. Now some of you will say, well, you know, you're cheating, because what will happen if we have day-ahead markets? Right? Maybe day-ahead markets are going to solve everything. So the answer is simply no. Day-ahead markets will just mitigate some of the effect, and even that is going to be not significant. And then the third question is, how much wind can we have? So we have done quite a bit of experiments here with our data from real markets, especially from PJM and ERCOT. And our general conclusion is that at 20% penetration, there is a cliff. After that, things deteriorate very, very quickly. Maybe you can get it a little bit higher, but not more than that. And at this point, basically, for every new megawatt that you install, you need to have every wind megawatt, you have to have another megawatt of oil or gas. This seems to defeat the purpose. And then the fourth question is, should we have differential price classes? And the answer is yes, big time. In the example, what I've showed you here, you need two prices. But in general, you probably need more than that for different classes. No, it's not popular, but this is what you probably need. So what I'm going to do now is I'm going to briefly go over a slightly different model that is very relevant as somewhat different hammer. So far we talked about a single producer, a single consumer, a wind producer, and an ancillary producer. So we had 4 entities here, and that's it. But you can ask, well, what will happen if you have multiple players? So each with different dynamics, incentives, and price curves. So what will happen then, especially if you have hundreds of even thousands of such players? So what is going to happen? Are the prices going to oscillate, explode? Will it be chaotic? What will happen? Is such a system even sustainable? So this naturally leads to a game theoretic approach. We have agents that are coupled by price function. The price function is what we had before. Stochastic depends on what they do, what all the other players are do, and you basically need to figure out how to track the actions of all other players, because this is a game. This is a game, so you need to know what everybody else is doing. Well, this is probably not possible. What might be possible is that you might get to see the price. A single price that you get to see announced all the time, like what happens now in all ISOs. So you see a single price all the time. So this calls for a dynamic game. you have the suppliers and consumers, presumably many of them. Each of them have its own process, which is dynamic. So like what you have today in ISOs, each producer or consumer declares a price curve. So it tells you how much I'm willing to buy for which price, or alternatively how much I'm willing to sell and for which price. So there is a market clearing mechanism, and then the common price is determined. So just to show you how the equations look like, we still have friction. So we have, but the change of there is a change in for the consumer, there is a change in the demand, there is a change of the supply that they get, and change of the price that they bid. That's for consumer, that's for suppliers, and the price, I'm not going to go into notation, but the issue here that is important is that you take into account all the prices, or to be more precise, all the price curves, and clears this market. So each of the players really bids a price curve. Okay, so and the loss function are exactly as they were before, and we have here the cost function that are also the same as we had before. So this is the same model that we used to have, but now we have possibly many players. So the issue here is that solving a problem for a single agent is pretty easy if we ignore the other agents. But solving for all of them together is very complicated. So let's try to do something which is, we can't solve the full problem. So let's try to solve something which is a little bit simpler. Every agent just looks at itself, and it says, I know what is happening to me. I can optimize. So the question that we ask is, if this player is doing this best response thing, I optimize for myself, and everybody else do whatever they want. That's one approach. The other approach, I'm going to solve the full game. So I'm going to try to reason what the other players are doing. And then I'm going to try and solve and find the Nash equilibrium. So now we can write again fancy math, HJB equations, and basically we had a similar thing before. Now the only difference is you bid price curves. So you can compute the best response for a single player, and then you can solve the control, and you can show that the Nash equilibrium exists, is unique, and is attained by best response, which is not very surprising. But computing it is very tough, and it's become just tougher with a number of players. So the question is, well, okay, so we know that the solution exists if you're happy with a Nash equilibrium. So, but we know that we cannot compute it, or it's going to be very hard to compute it, the same way that it was I think 2 talks ago, so it's NP hard. Okay, so what do we do? So now we say, well, we have hundreds of players. Let's go all the way. We have infinitely many players. And now each player just sees its own state and the global price. And the player assumes that there is some expected distribution of all the infinitely many players. And we try to figure out what will happen. Okay. So now what we had before, we have the HJB equations, the Hamilton-Jacobi-Bellman. Now we have something that is also called Fokker-Planck-Kolmogorov. I'm not explaining what it is. What it means is that there is a distribution of the state of every player, and this distribution which progresses in time. And the only thing that you need to take from this terrible slide is that everything here is deterministic. So we took a stochastic problem with infinitely many players, and because we look at the limit, we can think about it as a deterministic problem. Everything here it may look complicated, but it is deterministic. Okay, so again, we cannot solve the general problem. What we can solve is the LQG, so quadratic cost and linear dynamics. And it gives us equations which are deterministic. They look a little bit simpler, still pretty complicated. Again, don't remember it. We cannot prove Nash anymore. What we can prove is that we have epsilon Nash. So what does epsilon Nash mean? Epsilon Nash means, it means that every player can deviate and can benefit a little bit, but not more than epsilon. So you cannot then benefit by much. And whenever we have this situation, then we say that we are at an epsilon Nash equilibrium. Okay. So the theorem that you get, ignore the less important part. So you can solve the mean field equations, and you can get epsilon Nash equilibrium for the players. Okay, so this is provides you a very easy recipe. You want to figure out what to do, don't think about other players, just think about yourself and what happens to the price. And if there are enough players, things are going to work out well for you. And there is no benefit in gaming here. So let's just see simulation. So this is an example where there are 100 suppliers and 100 consumers. They're all identical. And the valuation here varies. Here, this is like the valuation varies with time. And what we see here is the convergence of all the players to the same bids, basically. Eventually, they all bid together the same number. So we see price convergence here. The thick line is the mean field, or the mean of the mean field, and the thin lines are just different players. This is just one simulation. Okay, this is trying to compare what will happen in a finite setup and in a perfect information exchange where you actually try to solve for the Nash equilibrium. And we see here the price, and we see the behavior of all the many players, consumer and suppliers. As you can see, there is no real difference. So once you get to 200 players, it's basically the same. So infinity is 200. Okay. And that's to conclude, so what have we learned from this model? And then, take it with a grain of salt. This is a model. Nobody says that reality behaves like that. So there is a volatility efficiency trade-off. You will never be able to get both efficiency and non-volatility to the maximum. If you want to have wind energy, just be prepared to face a cliff. As I said, in our simulation, it's around 20%. That seems to be the number that is very hard to improve upon. You should probably have multiple prices in your system. Ancillary and normal is better than not ancillary normal. But if you have different generators with different ramp-up costs, they should probably compensate differently. If you have large population, everything is going to be okay. It's going to be more stable. It's not going to oscillate. And you don't need to have information sharing. So you don't need to know what the other players are doing exactly. You just need to see the price. And that's something that we want to do. And from those, I want to emphasize one thing, and that's price shocks. So price shocks are a very interesting phenomena from a game theory perspective. We observe them in all the markets that prices spike up to huge numbers, and they're very hard to model. I'm not even sure why they happen in some of the markets, but presumably it's not gaming, but that's for the regulator to decide. That's it. I'll be happy to take your questions.
There's one thing that's, one result of yours, there must be a time missing. So I know, that I looked at a similar model with ancillary service, where I had both ancillary service and primary service, but you could show. And, it's a special case of what you're talking about.
Right.
There, the competitive equilibrium was unique, because it was a stochastic control problem, and the ancillary service was always there.
Right.
And so, if you get rid of that ancillary service, it's not the competitive equilibrium anymore. So you have to have an efficiency loss. So you're not really competitive equilibrium with this, or?
No, so there's no problem with that. So there's no contradiction. You maybe should take it offline because it's going to become a technical discussion. But basically, the uniqueness of the equilibrium is under some restricting assumptions on the dynamics. So, and again, I said in the beginning, I gave my warning initially. If you don't like the dynamics, don't like the conclusions.
Anybody else? No. One more.
Could you talked about the efficiency volatility trade-off.
Yeah.
Of course, one could have drawn a utility and a difference curve on that. But that and said, well, I prefer efficiency. I prefer volatility reduction. But one has to, I think because this is an inherent problem with introducing more volatile prices half-hourly or every 5 minutes. The question is the materiality of the volatility. Okay, as the accountant at the firm with one of these pieces of kit on the market. I don't care about the 5-minute volatility. I think so you put up two plots of volatile prices. Well, looking at them, as an economist, one would say, well, are they actually different materially?
So I mean.
So it could be. So in other words, I think you need to think about the actual resolution.
Yeah, I absolutely agree.
More volatile on a daily basis or a monthly basis.
Yeah, so I absolutely agree. The answer is that some of the processes are scale-free. So the answer will be yes, it will be more volatile on any scale that you would look. Maybe you still don't care if it's more volatile on a daily basis because it's still not going to be hugely volatile. However, there are other people that do care about price volatility, and they put price caps. So PJM, ERCOT, they have price cap on the day-ahead market. Sorry? I'm just saying people care about that. I'm not sure why, but they do.
Removing the caps because volatility might be necessary.
No, I agree. So volatility is necessary to obtain efficiency. That's yes.
So you are considering single bus policy.
Right. It's the math is not so simple even for a single bus.
You say like the wind is not controllable. So what does it mean? Because the wind blows, the power is just as much as it usually you should have to use it.
Right. So the wind blows, you have as much power that that is produced. You have no control over it.
In practice, the wind is dispatchable.
What do you mean? You know someone who can control wind?
Yeah, you have volatility wind up, but you can dispatch it.
To some extent, that's true. But by and large, the wind farms that I'm aware of are not very, very controllable, and they're certainly not affected by the price. So the emphasis is whether demand and supply are certainly affected by price, but wind supply is not strongly affected by price. And this is something that you can change the model, but the issue with intermittent energy, wind or solar, is that there's just, it's just there. There's not much you can do about it, and I agree that sometimes you can do things like tilt the angles or slow things down, but still, this is the essence of the intermittent energy, that it's stochastic and difficult to control.
It's more curtailing than dispatching.
Yeah.
Because you have ability to control,
Right.
Yeah, but
regardless of your no cost.
But again, if you're no marginal cost, only if there's a negative price would you voluntarily curtail.
Right.
And that's why perhaps you see negative prices.
Right. Yeah.
So it's price taker, but it's still dispatchable, which means the curtail is different terms.
Yeah, definitely. Yeah.
And then does this one affect it more than just my question? If you consider wind is dispatchable, you randomly select the maximum output of the wind. And you had another simulator there, so that as an up-on, you control that is not affected.
As was said here, if as long as the prices are positive, you would be a price taker. So assuming that the marginal cost is small, you would just try to produce as much as possible. And once you go negative, or go to very low prices, then sure, you're right. But then this is sort of the not really interesting regime, where the prices are very low, then you don't really care.
I like low prices.
Well, not if you're a generator.
That's true. Wow, yeah.
Is that one like the real price?
Any other questions? Real questions instead of just? Okay. Thanks.